So how can we determine if a sequence converges or diverges when written differently? Let's find out. This particular equation tells us how we can write out our sequence. But does it converge? Why don't we graph it and find out? So this is our first position. That's our second position, third. And if we keep going, what do we notice is happening here? It seems like our values are really, really close to zero. And it might look like we're exactly at zero. But if we zoom in a little bit just to see what's going on here, we'll see that our values are hovering just a little bit above zero. And as we go out even further, what's going to happen? So if we continue this process, we're going to see that we're still pretty close to zero. So does this sequence converge? It looks like it's getting very close to zero. But is there a short way that we can get this information? Remember that when we talked about going out to infinity for these kinds of functions, we use this Bobo-Botten East DC. And each of these represents cases of how to find a horizontal asymptote. Bobo is basically bigger on bottom zero. So an example of that could be this function, 5x cubed over 3x to the 7th. Notice that the power in the denominator is larger, it's bigger on the bottom. So that means that we're going to get larger and larger numbers on the bottom, and so this function is going to approach zero. When we look at 2n squared over 4n cubed, 3 is larger, so it falls into the category of bigger on bottom, so 0 is what it's going to approach. So that's just one strategy on how we can quickly find our information on convergence. And remember, when we plotted these points, it approached 0. So could we use the same strategy on this particular setup? So let's try it out. When we look at the powers here, what do we notice? They're both 2. So the exponents are exactly the same. So exponents are the same. That's this blue category here. Exponents are the same because they're both 2. That means that we're going to have to divide the coefficients. So we'll divide the 8 and the 3. So that means that what we're going to do here is we're going to state that according to our strategy, this should converge to 8 over 3. But let's see if that's what's actually going to happen here. So basically, we're saying that each of these cases here, Bobo, Botten, or East DC, should tell us how a sequence converges, or if it does, if it's written like a fraction. So if we graph this, this is what it would start off at. For n equals 1, we would have a negative number. For n equals 2, we have a positive number, and this is the pattern of what we would have as n continues to get larger and larger. We said 8/3 was our convergence. So why don't we test that out? We're going to put in 8/3. That's what this line here represents. So as you can see, as we get further and further out, we're not getting to be equal to 8/3. It doesn't equal 8/3, but it gets very, very close to 8/3. So this sequence appears to get very close to 8/3. What about this sequence? Does it converge? Remember that we're dealing with a fraction here. And so because this is a fraction, we can use what we know about rational functions, our Bobo-Botten East DC acronym, to figure out whether it converges or not. So if it's bigger on the bottom or bigger on the top, it's going to fall into one of these categories. In this case, 3 is larger than 2, so we're going to end up with a bigger number on top, which means that there would not be a horizontal asymptote. In other words, the sequence does not converge. So Bigger on top, not converge. So bigger on top, it does not converge. Instead, we're going to say that instead of converging, we're going to say that it diverges. So it does not approach a certain number. We can very easily convince ourselves that it diverges just by graphing that particular rational function. So we'll notice here that as n gets larger and larger, it's actually the sequence values are getting larger and larger as well. So it's not approaching a certain number. In other words, we're diverging. What about this example? It's a little bit different. It's still a rational function, but notice that this time we have a variable as a power and a number as a power. So we're going to still think about which one's larger, but let's graph it to see. So let's say this purple point represents our 2 to the n, and this one here represents our 3n to the third power. So as n gets larger, look at what's happening here. The purple one appears to be getting larger faster than the black one does. So 2 to the n actually grows faster than 3n to the third power. And even if we chose a larger scale, it's the same thing. The purple point is growing faster. 2 to the n actually results in larger numbers than 3n to the third. So when we think about Bobo Bottom Eats DC, in terms of which one is larger, is it larger in the bottom? Is it bigger on the bottom? Is it bigger on top? Is everything the same? We know that basically our 2 to the n is larger, so it's bigger on top because our function is growing faster. The top function is growing faster. So we know that when it's bigger on top, it doesn't converge, it's going to diverge.